We will continue our discussion of conic sections by rotating their axes. So far, we have looked at conic sections that have a general equation like this, and all of their axes have either been parallel to the y-axis or parallel to the x-axis. Let's just go through and how could we identify the conic sections from their general equation? Well, first of all, if it's a parabola, only one variable is squared. If you go back to those equations, remember we either had y minus k squared equals 4a times x minus h, or we had x minus h squared equals 4a times y minus k. So only one variable is squared. So looking at that, the only way that that could happen is that either a equals to 0 or c equals to 0. In the ellipse, both variables are squared and both coefficients are positive. Remember we had this formula, x minus h squared, y minus k squared. And looking at those coefficients, which are here and over a squared and b squared, small a, small b, those coefficients were both squared, both positive, meaning if you multiply a times c together, you're going to get a positive number. On the hyperbola, we either had x minus h squared minus y minus k squared, or we had a subtraction sign and switched them, meaning that, yes, both variables are squared, but one coefficient is negative, so when you multiply that a times c together, you get something negative. And remember, these were the conics that are parallel to either the x-axis or to the y-axis. However, we're now going to look at ones that are not parallel to either axis. And what happens, the general equation now has this xy term. And that's what you have to be careful of. So no longer can you just look at the equation and say, oh, that's a hyperbola, parabola, or so forth. We have to look at this quantity. You may remember from the quadratic formula that that was the discriminant, the part that was underneath the square root sign. If it's a parabola in this form, then b squared minus 4ac will equal to 0. If it's an ellipse, that quantity is less than 0, meaning the quantity is negative. And then if the quantity for a hyperbola is greater than 0, meaning the value is positive. And that's how you can identify that conic. So let's take this example. It's written in this format, and so we know that a is 4, b is 12, and c is 9. So just doing this calculation, b squared minus 4ac, so that's 144 minus, I believe that's 144, which equals to 0, which means that this is a parabola. Pretty easy. Let's talk about that rotation for a minute. Again, so far our ellipses or parabolas or hyperbolas have been parallel to the xy coordinate system. Now we're going to have a new coordinate system with a rotation angle of theta. So we may have like an ellipse, maybe we go up 2 and down 2 and side to side 4, but we're doing it on a new coordinate system. I'm going to call that x hat and y hat, a little bitty caret on top of it, whatever you want to call it. We have to derive formulas where we can graph these and identify these according to this new coordinate system. Our theta is going to be constrained between 0 and 90 degrees, because if I rotated it 90 degrees, then I'm back to just x and y. How are we going to do that? Well, we have some formulas here that relate x and y to our new coordinate system, x hat and y hat. And yes, I'm saying the word x hat and y hat. If you want to see the derivation of these formulas, there is a nice video here. If you just watch the first 7 minutes, it's a 34-minute video, it's very good, but the first 7 minutes actually derives those formulas. In order to use these formulas, we need to know that angle of rotation, and it is given by this formula. Look at this carefully. This is theta, this is 2 theta. All right, and it's in terms of cotangent, which I know we're a little bit more uncomfortable using, but that's just what we're going to have to do. So this A minus C over B relates to that general format. I used a computer program to graph some of these rotated conic sections so you can see them. So here's the equation. It ends up being a hyperbola, and this is our x hat and y hat coordinate system, and you can see that it's parallel to the x hat one, and we need to know what that angle is. This one is also a hyperbola. We're going to determine that angle as well. How are we going to do that? Let's look at this first example. And in order to find the rotation formulas, we have to find cosine theta and sine theta. So the first thing we need to do is find the cotangent of 2 theta, and from there we can go forth. So the cotangent of 2 theta is A minus C over B. So A is 3, C is 3, and B is negative 10, which is 0. So I have 2 theta equals the inverse cotangent of 0. Now think about your graph. That cotangent graph was situated between 2 asymptotes of 0 degrees and 180 degrees. So where was cotangent 0? Cotangent 0 is at 90 degrees. But that's 2 theta. So to solve for theta, we divide by 2. So I have an angle of rotation of 45 degrees. If you go back and look at that picture, that pretty much looks like 45 degrees. So I think we did the math right. Now we need to find cosine theta and sine theta. So we know that the cosine of 45 degrees is the square root of 2 over 2. And so when I say exact values, that means no decimals. Go back to your chart, your unit circle. The sine of 45 degrees is also the square root of 2 over 2. So now we need to find those rotation formulas. So remember, the formula is x equals x hat times the cosine of theta minus y hat times the sine of theta. So just substituting those values in. That's one rotation formula. And then I have my other one, which looks pretty much the same. So what is y? The same thing in this particular case, except with the plus sign, and that's because of that angle of 45 degrees and sine of theta and cosine theta being the same value. So when I say find the rotation formulas, this is what I'm looking for. Let's look at example 2. Okay, so again, we need to find the cotangent of 2 theta. It's A minus C over B. So that's 10 over 10 square root of 3, which is 1 over the square root of 3. So the cotangent of 2 theta is 1 over the square root of 3, or you may have memorized it in your chart as the square root of 3 over 3. I know you're not liking that. You're just going to have to know when is the cotangent. First of all, remember we're restricted between 0 and 180 degrees. So first quadrant, second quadrant. First quadrant, everything's positive. Second quadrant for the cotangent, it's negative. So we know this is in the first quadrant. If I ask you exact values, you know it's going to be a pretty number. Right? So where is the cotangent equal to the square root of 3 over 3 in the first quadrant? At 60 degrees. Divide by 2. So theta, my angle of rotation, is 30 degrees. So the sine of 30 degrees, remember, is 1/2. and the cosine of 30 degrees is the square root of 3 over 2. So now we're ready to write our rotation formulas. So we have the cosine of theta square root of 3 over 2 times x hat minus 1/2 y hat. I just need to use a different lettering system. I can't keep using x and y. Some books use x prime. That's fine. Another book used this notation. It's just something to differentiate between the original xy axis and our new xy axis. So here we have the sine, which is going to be 1/2. Then we have plus the cosine. And that's our other rotation formula that we're looking for. So not real hard, except knowing your values for cotangent. Here we have this one. It's also an ellipse. We're looking for that angle and the rotation formulas. Now you're saying, why do I need those rotation formulas? If you'll just hold on, we're going to get to that. It's just a little bit more complicated. We just need a little bit of practice right here. What we're going to do with those rotation formulas is we're going to substitute them in and find the actual new equation in terms of our new coordinate system. So again, we need to find theta. So the cotangent of 2 theta is A minus C over B. So we have -1 over the square root of 3. Or again, you may see it you may have memorized it like that. Now that tells you that it's negative, which means that it's bigger than 90 degrees. It's in the second quadrant. So where is the cotangent equal to negative square root of 3 over 3? That's at 120 degrees. So theta is at 60 degrees. That looks good. So what is the sine of 60 degrees? What's the cosine of 60 degrees? And then we would write our rotation formulas. So we have the cosine times x hat minus the sine times y hat. And here we have the sine times our new x coordinate plus the cosine times our new y axis. So not too bad. Now notice, those are our 3 special values for theta in the first quadrant. I did an example where theta was 30 degrees, an example where theta was 45 degrees, an example now where it's 60 degrees. That's it if I ask you for exact values, being able to use that chart. But not all those angles are that pretty.